In this video I'm going to talk about the sum of the squares of the first n Fibonacci numbers. So as a reminder, the Fibonacci numbers are defined recurrently. So we have the first two Fibonacci numbers equal to 1, and then we have the recurrent relation that says that the next Fibonacci number is equal to the sum of the two previous Fibonacci numbers. Also as a reminder, in one of the previous videos I proved an identity that the sum of the first n Fibonacci numbers can be expressed as another Fibonacci number minus 1. So in this video I'm going to prove an identity about the sum of the squares of the first n Fibonacci numbers. So it says that this sum of the squares is equal to fn multiplied by fn plus 1. So the proof is going to be by induction. So the proof by induction. So first we check the base case, the case n equal to 1. So on the left side we have f1 squared. On the right side we have f1, f2. So both f1 and f2 are equal to 1, right? So so here both the left side is equal to 1 and the right side is equal to 1. Therefore this is true. This equality holds for n equal to 1. So now we suppose that the equality holds. Suppose that that the statement is true. It is true for n, and we consider it for n plus 1. Consider for n plus 1. So let's write the statement for n plus 1. So we have f1 squared plus f2 squared plus and so on plus fn squared plus fn plus 1 squared. Allegedly this is equal to, we need to prove that this is equal to fn plus 1 fn plus 2. So now we notice that the first n Fibonacci numbers can the first n terms can be well, okay, so let's do it carefully. So this is the equality that we need to prove. So now we start from the left side. So we write again f1 squared plus f2 squared plus and so on plus fn squared plus fn plus 1 squared. So now we notice that the first n terms are exactly as what we have in the, like on the left side in the equality for n, which is which we suppose is true by inductive hypothesis, so we can replace it with fn plus 1. So this is by inductive hypothesis. By inductive hypothesis. Plus fn plus 1 squared. Right? So the last term we write as is. We keep it as it is. So now now we notice that these two terms, they have a common multiplier, fn plus 1, so we can move it like this, fn plus 1 multiplied by fn plus 1, right? So now we notice that this sum is the sum of two consecutive Fibonacci numbers, which is by the original recurrent relationship, by this, it should be equal to fn plus 2. So here we write that it's equal to fn plus 1. This remains as it is, and this we rewrite as fn plus 2 by the original recurrent relationship. And so now we see that what we get at the end is exactly what we needed to get. So we look at the beginning from where we started, and look at the end where we arrived, and this is exactly the equality that we needed to prove for n plus 1. So basically this concludes the proof of the inductive step and the proof of the equality of the theorem.